Good morning, everyone. Welcome back to Aggressive Mastery. These dev vlogs are going to become a little bit easier for me. I don't know how that's going to happen, but I'm going to try to just record this in 10 minutes, and then we're heading to the park. I've been very busy since the whole time since you last seen me. We made a lot of really cool improvements. Today I'm sharing with you how to export your particles from Niagara back to blueprints or C++ and render them using instant static meshes, ISMs, as Niagara or nanite particles. So you can do Nanite Niagara particles. You could do this easily for static meshes, which is what I'm doing it for. And then I'm also going to look to expand it into any effects that I can use a cutout for, or what's that called, a masked material, so that we can also do nanite there and see how that works. But I haven't done that yet for the effects, only for the static meshes. What you see running behind us, or behind me, will make me a little smaller too, is 100,000 particles of one out of 33 different meshes that are being exported every frame to blueprints and then being sent to a custom C++ node that does the conversion from particle position, rotation, static mesh, and scale into a transform that I make transform arrays out of based on those mesh indexes and update every second. In C++, inside the editor, which we're seeing right here, is about 60 frames with all 100 particles being exported once a frame, colliding with mesh distance field, global mesh distance fields within Niagara as a GPU collisions. And also that lets us collide with 144 Unreal logos, these gold ones, which are actually just simulating static meshes that also are generating mesh distance fields. So right here you're seeing the rendering. Let's look at a pure nanite scene, and then we'll look at the collisions of mesh distance fields. So here's the triangles. I do have rotations working, so we'll look into that and see why it's not updating rotations in just a second. And then now also we'll head back to the normal view here, and we'll go ahead and look at global mesh distance fields. Global mesh distance fields. So this is what the particles are colliding with, which are these walls here that are just sort of keeping them in a trough. And then we have mesh distance fields being sampled lightly by the global mesh distance fields. And there's a whole bunch of things you can do to modify how your mesh distance fields generations are done and how fast they're made, such as reducing your per mesh voxel density and also the mesh distance field detail. There's also overall project setting for mesh distance fields that you can reduce. And one of the most impactful settings is actually to reduce in the console the size of the voxels that go into mesh distance field generation. Default size is 0.5, so anything bigger than 0.5 of the voxel size will be included in the mesh distance field generation. I turn that up to like 5, voxel size 5. If I really need to exclude some things in mesh distance field generation, but still get large objects collidable with. So that's some deets for you. Also, this box, that feels like an editor crash right there. The box is generating mesh distance fields, and I'm gonna pause the video for. Be right back. So yeah, we're back. That was a little bit of an editor crash. Swapping between the different debug views is asking a lot out of what we're doing after all. Alright, so how do we do this? And why we do this? The reason we do this is, let's do a stat unit. We're getting 86 draw calls for, 120,000 moving simulating objects. That's pretty cool. 83 draw calls. That's pretty cool. That's why we do this. It should, and we're rendering at 60 frames a second doing so. That's why we do it. All right. Now, how do we do it? You can go to the, what is going on? I think, stop. All right, you can go into the content samples. This has been able to be done on the GPU Niagara system since Unreal Engine 4.27. Of course, that was about the last Unreal Engine 4 release, so it wasn't very well known, especially by me. I don't even know if I ran 4.27. And then it was in 5, is what I've been told. I didn't find it till just like a couple months ago, or maybe a month ago, maybe 2 months ago. And then I've started integrating it into my systems. So how you do that is you can go into the content samples projects that come from Unreal or an Epic. You can go to the advanced particle level and go to the emitter 4.2, which is blueprint exporting GPU particle location to blueprints, something like that. What that's going to do, and here are my blueprints, so we'll look at these blueprints in detail, and also the C++ that they are converted into right now. So framework on how I set up the blueprints, just at a high level, is that I have an instance static mesh component for every single mesh type that comes from Niagara. So I have 33 of them, or 32 of them. 33, so 34 of them, I guess. I might need to add one more. And I just take all those, throw them into an array, you see here. So I have, at the begin play, I get all my rendering components, which these are all my Nanite ISMs, or instance static meshes, and I make an array of them, so I have access to them at runtime. I also set this actor, which is doing my updates, as the actor that Niagara will send the export data to, and that's done with this set Niagara variable of object. So what object? It's asking what object to report to, or actor. I put the self of this blueprint and it will be a variable name of readback actor inside of Niagara. And then I have my Niagara component, which is also in here as a root, and we'll look at that in just a moment about what goes on in Niagara. So this is a interface component to do Niagara readback, which is made by Unreal. And so to use that system to get these variables, I think you do need to add a class interface. There we go. And so over here, you're going to want to add the Niagara Particle Callback Handler. So Niagara Particle Callback Handler class interface. So you would just hit here, go Niagara. And I've already added, so otherwise it would pop up here, I believe. And then it would add in. That will give you access to this set Niagara variable particle system component here. Actually, that might be a normal thing that's in there, but you'll have to set it to readback actor because that's how Unreal has named that variable that it's looking for in Niagara. And we'll go look at Niagara real quick. Here's my Niagara system. It's just a default fountain that I'm using. And what you do is you have a export particle data to blueprint node, which you can add just by going to particle update, export, and it's going to be the only one that pops up here, export particle data to blueprint. It's going to have some variables over here, such as condition to export data. That if you just click on this export particle data, it's going to show you a graph. Now this is cool. This is how Niagara does its stuff, and more importantly, this is done on the GPU if you're doing GPU simulation. It has to be. I mean, just how fast it is. You're going to get this input here, this get map. This is getting variables. And one of those variables is condition to export. And that was an input variable. That's what the input pins here. Now, this won't be a whole Niagara example. This is supposed to be a 10-minute video, and we're at 10 minutes. So I'm just going to breeze through this. Hit me up on the platform previously known as Twitter as GameDevMicah with any questions, and also reply in the comments down below with any questions as well. Happy to help explain this all to you and get it working for you. if you need that help. Otherwise, let's go quicker. So you can go ahead and double click and dig into and see really what's going on. What I did that you do need to know about is I took in my particles mesh index here, times it by 1,000, added in my W, so world position part of my mesh orientation, so that now I'm passing out mesh orientation XYZ as my velocity. So I'm not getting the velocity out, I'm getting rotation XYZ out from my particle export. I then take the missing value from the quaternion and pack that together with my mesh index, which is what mesh I'm using for my particle system for this particle. And I'm sending all that back to Niagara. This is how I pack it. I take the mesh index, which is a 1 through 33 number, times it by 1,000, which is going to make it bigger. I then add the W, which I took the W, divided it by 1,000 to make it smaller. I then added a 0.1 because I saw that when I divided by 1,000 it would vary around 0, I believe from negative 0.1 up to 1.1. So by adding 1 it moves it out of the way. I add them together, and this is, I didn't explain that very well, but this is how I packed it a while ago. I add them together, and now I have a packed data value that I send out as size. So we get our position, which is just straight up particle position. We get our size, which is a packed value of the W part of our rotation, so that our rotation will actually be fully correct in the world versus the particle system when they match up. And our mesh index, which is what mesh it is. I pack those together as that scale value, float. And then I pass out the remainder of 3 values, x, y, z, as my velocity for rotation. That will be exported to an array, or be added to an array. And then you're going to see if you export, how often you export that array. If you do it every frame, then these things will only be in the array once a frame, so once in that array. If you do it less than once a frame, you could gather the same particle a lot in that array. So you got to manage that a bit. And you could do it inside the Niagara nodes rather than out in Blueprints or C++, and it would be faster. But I didn't mess with that. I'm just getting the data every second, or every frame, every tick. All right, so that's what we were looking at the exporting of the data. Otherwise, this is a default export that's part of the content example, is this sketch pad. I just am showing you how I pack mesh index and the rotation instead of using velocity output. And that will be important for, that's the work that we're doing in Blueprints that we're going to look at next here. So and here's my mesh. You can see my mesh render is disabled. And what I have over here, I don't even have any meshes for the other ones. Whoops, I'll have to go look into that. I thought I had cubes everywhere. Is it not? Oh. So does that mean that they're invisible? Let's find out. I think I have to stop. Pause. I'm going to pause, be right back. Okay, yes. I'm not rendering them because I haven't assigned the lower parts here, so we won't be able to see it in the window on the side. But I don't use the mesh renderer. I just have 33 numbers here because we're just picking the number. We're just picking the static mesh. So you manage your mesh renderer as you want, but we're not even using it. I can't delete it because I do need a mesh renderer index. So I have the mesh renderer in this particle system here, and it's disabled. But I do need it because I need to have 33, or I need to have my array over here to assign my particle a mesh index. So we don't even use the mesh renderer, we just need the array of mesh indexes to assign, so that when we're in here, we can go ahead and grab it right here. That's why. When you're outside and you're looking at this Niagara system, you'll assign the blueprint That is one of these next. So we have this condition to export. That's if it's going to export. That's going to be a bool. That's going to go with any other triggers you have on your export. One trigger may be you want to only export on particle death. That would be how you would export a particle that is no longer going to be seen or in the particle system, and you want to have it sleep to an ISM, is you would have your trigger condition be that the particle is now seen as dead, and you would export that data then to just a new system that just sleeps to an ISM, which is what I am already doing. So it works great. Delay between exports here, I have it disabled because that's going to be what would make things pile up in the array. So I'm exporting every frame, so I know each particle is only read in there once. And then it will start to ask you things like, what do you want to export as your position? So I left particle position as what I'm exporting as position. Then these other two, I actually depinned them. So you can see right here, I'm not using those inputs. And that's where I went ahead and added my additional inputs of mesh orientation and mesh index, which you can just do here. Mesh index is already in there. So is mesh orientation. I'm not going to be doing other mesh stuff. But I'd like to show you particle. Here's some, you could get color, particle color. And now we added particle color to it. I don't need that pin, so I'll remove it. But that's how you get the stuff out. So export particle data blueprint will export every tick, all the particles, because it's done in the particle update of our fountain. The interface here, export particle data interface, this is where we tie back to the blueprint. Callback handler parameter, readback callback actor, that's what we assign in the blueprint right here. Readback actor is getting assigned to the callback handler parameter. Your GPU allocation modes, I'm playing around with this. You do need to fit it, and there's a console variable we'll look at here real quick. I have it at 100,000 here, fixed. And in the console variable, we have fx period Niagara period ndi export period GPU max readback count. By default, that's 1,000, and I've upped it to 100,000 so that we can get all of our particles out in C++. All right, now let's look at the exporting portion of this, which is what you're going to get back from Niagara. Niagara is going to call this event once you've had the your blueprint attached to the interface for Niagara callback. And it's going to export an array of particle data. If this array of particle data in a future release becomes an array of transforms or a structure of transforms by a mesh index like we're doing right here, then great. Unreal's given us the easy button. Or, even more so, if they just make the mesh renderer Nanite ISM, then this all is for naught. So that's going to happen, I'm sure, soon. So, but right now what happens, this gets called, it sends out this array, and if we break it, I don't think we can break it here. I'll do a for each. I don't need to do it. What I'm going to do right now is I pass it to my C++ function, and it returns me an array, which I loop through that has a this is such a small screen. So Niagara sends out an array of basic particle data, which is what we exported in here. So we get our, right here, position, our pack size, and our rotation, which is called velocity, but we made it rotation. Comes out of Niagara. Closing Niagara. Closing this thing. Closing that thing too. I'm dedicated to the big screen. That data comes out, runs through the C++, comes out of C++ as an array, or a structure of transform arrays, which, depending on which index of the structure array they are, matches their static mesh. So then we get the index that they are. We get our ISM Nanite arrays that we're going to be updating every frame. We clear it, and then we add all of our instances as just one big bulk add. Make sure my head's not blocking it. And that's what we do every frame. Since it's being called every frame, we clear every frame. But if you wanted to throttle it, you could. You could put a delay node right here, or some sort of a throttle right here, and only do all this stuff at the frame rate you want, which would give you like a stop motion look to this. Now in blueprints, well, in C++, here's the C++. I think I can make this screen bigger. We'll say 200%. We're going to export a transformer or an array of transforms. That's a structure, so a structure of transform arrays. Our library name, we're going to go ahead and take in an array of basic particle data. It's called Niagara export data. The variable is defined here, creates the return list of transforms to be sent out by mesh index. We get our transforms here. This is a local loop transform that we're going to build for each one. And then we have our mesh index, which is an int32. For each, so we come in here and say for each particle data that we're getting in, go ahead and grab the location and just set it to my export position. Grab the scale, and I'm actually just hard setting scale. And then for right now, we can add that later, so you just add in your own scale stuff. We grab the rotation, and this is where it gets hard, right? We want to make a quat, which is 4 floats. We're going to set the XYZ, which we can just grab from our exported data that we're working on here in this loop. And then we're going to depack the W portion of it. So we'll take the export data size. Long we'll remove the small part and just leave the big part after on the decimal places and fractions, so that we give you the whole number and get rid of your fractional part. And then we minus 0.1 to flip it back over and have detail there. But this is all about just getting that one piece out. And then we normalize the rotation. What that's doing is it makes sure none of these values are above 360 in rotation. If they are, it crashes. So you normalize the rotation that we just rebuilt. We take the mesh index by getting the long of take the value, remove the other side. Oh geez, depacks the mesh index by store. Long parentheses. I'll break this all out. You know how that works. All right, and then if we have an invalid mesh index, then we need to add a new array to our structure, because this is where we're creating that structure of transforms array every time we run this. So this is saying, hey, do we have this mesh index? If we do, we're going to add ourselves to that transform array. If we don't, we're going to create that transform array and then add ourselves to it. And then once we're done with going through every single particle that was exported, so we do this with 100,000 particles 100,000 times. That's why it's hard in blueprints. We go ahead and return that packed array by mesh index. And I'll show you the header as well. I think I have it. Oh, there it is. And that's just defining my Niagara export data. So what the structure I'm going to export is should just have a array of transforms. So it's a structure of an array of transforms, and then I make a array of this structure, which gives me an array of arrays. And then down below, we just define the class to take in a particle array and return that structure of array transforms. If you can read it, then I'll scroll over here so you can get the other part. Cool. All right, so that's with blueprints, or that's with C++, which is what this node's doing. Now to do the exact same thing in blueprints, I'm going to go actually turn down how many particles we spawn, because I'm afraid of what's going to happen. No, we'll do it. Let's just do it. All right, click. So just by doing that, I take my event here. It's being called by Niagara every frame, and I move it from driving the C++ that we just looked at over to driving that data through blueprints. So what we're going to do with driving that data through blueprints here is take in the array of particle data, get the length of it, take our exporting array of transforms by mesh index that we're going to build, and resize it to 33 so we have all those values to add to. So this would be that last part of the C++ where we were checking to see if the mesh index exists. Here we're making sure the arrays exist. We come in here and we're doing a branch for our loop. The reason behind all this, instead of using a for each, is that this is a special built loop using just the right variables, instead of using blueprints generic for loops which are slower. So I've stripped this to hot rod it as fast as possible to do what I want to do in blueprints, and we couldn't get it fast enough, so we had to go do it in C++. So that's why we're not using a for loop or for each loop off the array, is because it's slower. I think it just has to do with how it's accessing variables, how many nodes there are in it, and I did a lot of Unreal Insights, which we'll check here and do here to compare these two right after we go through the blueprints. So, what's up, Lucy? There's Lucy. Lucy had a big growth on her jaw, and I was worried that it was cancer. We've been working on that, and we took her to of course, taken her to the vet. She's had surgery. It's been biopsied. It's not cancer. It's a big infection. We're super happy. She's recovering extremely well. The swelling's like almost completely gone. She's 15 and a half years old, and my studio found her, so I couldn't be more happy. That's why I'm doing this video right now too, is to share something before we head to the park. So yeah, lots of fun here. I hope you can use this in your systems as well. So Niagara kicks out the information we were looking at, the particle data. I set it as a variable here. I try not to set any variables down in C++, just trimming out any of the unneeded calls. Same thing in blueprints, but we need these calls. So I set the length. This is going to trigger if I loop or not. I reset my export data. We come into our branch and we start looping. We'll come over here, we're going to grab our data that's been exported, and then I'm doing my dpacks. So dpack the mesh index, remove the W rotator. So we get our size out on top, and we remove the fraction of it. So the stuff on the other side of the decimal. We then divide by 1,000 to rehydrate to the correct value, clear it to make it expected a float int 32, so that doesn't have any remainders, and then we can grab the mesh index by it. Likewise, when we build the quadrillion below, we take the XYZ, put them right in XYZ on the quadrillion, and we rebuild the blueprints by taking the fraction, rehydrating it by taking 0.1 away from it, and timesing it by 1,000 to put it back in its correct value. And then we make the quadrant. Then we convert it to a rotator. And then we have scale as just a hard set value I'm using, I believe, as like 1 or 0.2. So you just plug scale into another one of these exports or pack it into something somewhere, will be what I'm doing. And then we increase our loop count, come back around, make sure we're still within loop, and do it again. And this way we're going through and depacking the mesh index, the rotation, and taking the position and adding them into this mesh index transform array, which is just a big array of empty transforms. So once we build that together, that's going to be what we render. Once you're done with that, we reset our loop variable, and then we update the ISMs by doing an update ISM call, which I just put right here to match up my rendering updates to each other from C++ and blueprints, so you can see how we render is pretty much the same. So when we get our data done via blueprints looping, we now have this mesh index, which is 33 arrays of transforms that we need to update every frame. So we'll just do a loop, grab the, and it's only going to loop 33 times, so it's not that big of a deal, where this is looping hundreds of thousands of times. So down here we'll grab our nanite array by the index that we want to update, clear the existing instances, take the array of transforms that we generated up here for that mesh index, and add those in. I'm going to play around. Since Nanite does not like to overdraw with other Nanite mesh, if you're doing this and you want to do batch updates without the clear, you're going to have to pool your extra instances somewhere, and if you want to say pool those at 0 and 0 is visible, you're going to have a lot of issues because you're going to have a whole bunch of pooled Nanite meshes sitting right on top of each other in view. I'm looking this. What I think you can do about that is use per instance custom data and drive a material to make those pooled instances completely transparent or fully cut out via masked or fully masked. If that works, then that would mean that we could basically make the pooled instances invisible by their custom data through the material. I'm not sure how well a masked material versus a non-masked material for everything really will run with Nanite, but we can check it out. But that would be one way to do that if you wanted to do batch updates instead of this. So naturally, that means I looked at both of these ways otherwise, and this is faster. Because what happens is, if you don't. Okay, park's in 10 minutes. I'm almost done. Thank you, Logan. So, and on the C++ side, we get the data out, we go through a loop, we clear the instances, and we add them. It's the same thing there. So there, I think, is it. I think we talked about it all, and it's about half an hour of the full details on just how to spit out Niagara instances, Niagara particles every frame, and then do an update. Now, let's quickly, we never hit play, right? I'll save everything, which probably isn't the best. Hit play. So we're going to see about doing 100,000 via blueprints now. So we were getting 60 frames. Oh, widget reflector, leave me alone. All right, so with C++, we were doing 60 frames. And you can see here 100,000 or 200,000, we're going to be doing 9 frames. Let's look at the Unreal Insights real quick on that. I'll hit my record here. We're doing some tracing. I'll actually stop the simulation, stop the tracing. And it's hard to see Unreal Insights on a 4K. But here is what's going on. You can see that this is one frame. This blue area right here is one tick. And there's this big pink bar. This big pink bar right here is our Niagara system kicking out all those particles and then converting it in blueprints. So that's taking 92 milliseconds, it says. Was that really it? Yeesh. All right. Well, I guess that makes sense. 9 frames a second or whatever. Does it say 9 frames? Yeah, it does. Okay, so yeah. Now let's do it with C++. So we're going to do the exact same thing. We're just going to drag this down here, which is just because I like to organize it. Now we're just going to run it through this C++ to do all of this. And you can see we're at 100,000. Or, well, 60. Let's go ahead and start recording it. Do it like that. And what you're seeing with my frame rate, the M frame rate that's our minimum frame rate. So what that does is every single second, or every single tick, it takes delta time, and if it's lower than any of the ones it's had, or rather it just stores it in an array. It just takes the tick, the delta time, and stores it in an array. Once a second, or once my regular, only doing updates about 10 times a second for the frame rate. So the one on the bottom is what it is on average, and the one on the top is our minimum one in every second. So if we've never dropped below 45 frames per second on any frame, or 45, yeah, on any frame via delta time, where the lower one is every frame's current. So on average, you're going to see 60 plus with what I'm doing right now, but sometimes they dip down to 45 on one frame. That's like I'm trying to make things harder on myself, because if about stutters and smoothness in games, it's about when you are on those minimums. So if we never dip below 60 frames a second on that minimum, and here you can sort of see maybe, well, just like it's not smooth. So I'm seeing what the lowest and the highest are on this bar via that frame rate. But let's go try and find that work. It's right here. So now we've turned that into 4.1 milliseconds. So we went from, 90 milliseconds to 4.1 milliseconds in blueprints going to C++. And the reason is overhead. Actually, sorry, 1.8. 1.8. That included the 4.1 included all the ISM updates. So 1.8 is actually just the conversion. All right, thanks for hanging out on this long one. I hope it was fun. I'm heading to the park with the kids. Lucy's been hanging out on my lap. We're super happy. I'm going to hopefully have the next one be a more complete, here's getting particles in, plus the particle, this one is the rendering of particles as nanite, and then particles out. So we'll look at that stuff too. Thanks for joining me. Hey, follow me, subscribe. We got more stuff coming. I need the help. Ciao.